Start doing a problem, cooling tube design problem in the transformer unit. Unit number 2, transformer, where we are going to design a cooling tube, number of cooling tubes required and position of the cooling tubes. Both the things we are going to design. Now the problem they have given the capacity of the transformer is 250 kVA, 250 kVA. And total loss they have given us, this is small Q, which is equal to 4800 watts. And the temperature rise, permissible temperature rise, they have given us 25 degrees centigrade. And the primary voltage is 6600 volt and secondary voltage is 400 volt. The height of the tank, transformer tank is 1.25 meter as mentioned here. And width of the tank is 1 meter or 1000 mm. Length of the tank is 0.5 meter or equal to 500 mm. And it is a 3-phase core type. I think this specification is the typical specification of a distribution transformer. And the cooling tube specifications are diameter of the cooling tube is 50 mm and length of the tube is 1.05 mm. Now they have asked to identify the number of tubes required and how to position them. That's what we are going to see. Now, we know that if this is what the dimensions of the transformer tank, dissipating surface of the tank is nothing but air will be flowing on the vertical walls of the transformer tank, which means that here is WT and this is HT, height of the tank. So you will be having HT, WT on this side and HT, WT on the back side. And similarly here, LT into HT on this side, right side, and LT, HT on the left side. Which means that there are two HTs are involved. That is, you have 2 into WT plus 2 into WT which means that 2 HT can be taken out. Then it becomes WT plus LT, 2 HT into WT plus LT. You substitute the values. This is 1.25 meter, this is 1 meter, this is 0.5 meter. So we get totally 3.75 meters square area. Surface area of the tank is this one. Only the vertical surface area. In a cooling tube design, the transformer tank cannot dissipate the power from the bottom area of the tank. It is not possible because it will be dissipating only in the upper side, from bottom to top. So from here you cannot get the heat dissipation. On the top side also, the chances for air falling on the top side will be very, very minimal. So generally they neglect this particular area of top side. Unless otherwise they have specifically mentioned, you don't need to calculate this one. In some cases, they have asked you to identify only half of the area as useful area for heat dissipation. In this problem, we are calculating only the 4 vertical surface areas of 4 vertical sides, which yields to 3.75 meters square. Now, what are we going to identify? We are going to identify the number of tubes. Number of tubes is nothing but total amount of cooling tube area. Cooling tube area, let us assume XST. What is ST? ST is surface area of the tank. Surface area of the tank. And the XST is cooling tubes area. We are assuming cooling tubes area. We are assuming a portion of the surface area of the tank is assumed as cooling tubes area. அதாவது இது ஒரு 10 meters square அப்படினா அது ஒரு portion, it may be 0.5, it may be 2, whatever it may be. X may be some value in the surface area of the tank, it will X times cooling tube area. If we identify this one, then the number of tubes required is XST divided by individual cooling tube area, which is nothing but pi into dt into LT. dt into LT. What is dt? Diameter of the tube, which is equal to 50 ohm. LT is length of the tube. In this problem they have given 1.15 meter. So pi dt is surface area of one single cooling tube into LT is total surface area. This is cross section area and this is total area. Then you add, then you get the total surface area of an individual cooling tube. This is total surface area of cooling surface area, total area of cooling tubes divided by individual area, and you get the number of tubes. Now to identify this XST, we have to use this formulas. Now there is a formula which states that the temperature rise temperature rise, theta is equal to total loss that is 4800 volt, and total loss divided by total loss dissipated. Now, if both are equal, then there will be 1 degree rise. If this is small, the temperature rise will be higher. If the total loss is 4800 watts per second, the loss dissipated is very high, and that means temperature rise will be not be there. It will be minimal. So the total loss we have already given is 4800 watts, and total loss dissipated you have to calculate. There are two modes of heat dissipation. One is by radiation. That is equal to 6 watts per meter square area per degree centigrade, and by convection, which is equal to 6.5 watts per meter square degree centigrade. These two are very constant. It will be constant for every problem. And due to the provision of cooling tubes, the heat loss due to convection is increased by 35%. That is also they have given. In the problem they have given the increase in heat loss due to convection due to the presence of cooling tubes is 95%. Which means that for the surface area of the tank, you get heat loss due to area of the tank. Heat loss due to the surface area of the tank. Is equal to 6 plus 6.5 into ST. This is equal to 12.5 ST surface area of the tank. Now, increase in convection, heat loss due to cooling tubes is equal to 6.5 watts. Radiation you don't need to calculate simply because radiation on the, if there is a tank, you're going to place the cooling tube here. So this cooling tube will be covering up the inner side radiation. So it is better to calculate only due to the convection. So heat loss due to cooling tubes is 6.5 into 35% increase, that is 135 divided by 100 into XST. XST is area of the cooling tubes. So heat loss due to the cooling tubes area is equal to this. This is roughly equal to 8.8 XST. Therefore, total loss dissipated is equal to, let us assume this is 1 and this is 2. You get 1 plus 2, which is equal to 12.5 ST plus 8.8 XST. Now, what is this? This is total loss dissipated. So this can be rewritten as total loss dissipated. Total loss dissipated is equal to ST, you take it outside, you get 12.5 plus 8.8 XST. Now, from this equation, temperature rise, that is nothing but theta is equal to total loss, which is nothing but 4800 watts, divided by total loss dissipated, which is equal to XT into 12.5 plus 8.8 XST. You substitute all the known values. Let us rewrite this equation 3 as you take this 12.5 plus 8.8 XST is equal to 4800 divided by theta ST. So here already ST is there. ST has been taken out, so this is 12.5 plus 8.8x only. So here this is 8.8x. 4800 divided by theta into ST. This is equal to 12.5 plus 8.8x. Therefore, x is equal to 4800 divided by theta into ST minus 12.5, and you divide by 1 by 8.8. Take this 12.5 to the other side, you get minus 12.5. 8.8 take to the bottom side, you get 1.8. 1 by 1 divided by 8.8. Now we substitute the values. This values gives 4800 divided by theta. Theta here is 35 degree into surface area I have already calculated, that is 3.75 meter square minus 12.5 into 1 by 8.8. The value goes to 2.7431. X, the proportion of x is equal to 2.7431. Now, if you know the XST, XT is known, X is known, pi dt and LT is known, so we can calculate the number of cooling tubes. Because X is 2.7431 and ST is 3.75 meter square, and pi dt, LT, we know the values, we can substitute and get the value of LT. Now, from the known values, LT is equal to X into ST. X is 2.7431 into S is 3.75 meter square divided by pi value is 3.14 into dt is 50 mm. 50 mm is nothing but 0.05 meter into LT is 1.05 meter. You get the value of 2.7431 into 3.75 divided by 3.14 into, sorry, divided by 0.05 divided by 1.05. Which is roughly 63 tubes. The number of tubes will be approximately 63. You cannot have an odd number because you want to have a symmetrical structure, so it will be 64 tubes. So the number of tubes is supposed to be 64 tubes. Now, the number of tubes you have calculated, what you have to identify is, how you are going to place it. Now, you are going to place at the width and length of the cooling tubes. So let us assume this is the width of the cooling tube. Width of the cooling tube, where this is exactly width of the cooling tube is 1000 millimeter, and here it is 500 millimeter, 500 millimeter. This is length of the tube and this is width of the tube. Now you are going to place the cooling tubes. You cannot place the cooling tubes at the edges. You have to leave a space of 25 to 50 mm for individual cooling tube space. No, you cannot start at the edge. You need some space. So that space is supposed to be between 25 to 50 mm. This is on all the sides. Right? On the four sides. Now, how many tubes has to be there? Now, individual diameter of the tube. Diameter of the tube is 50 mm. Space between the tubes. Space between the tubes. Supposed to be 25 mm. This is constant one side. So, two tubes contain 2 into 50 mm and one space that is equal to 25 mm. So for every tube, let us calculate for 1000 mm. For 1000 mm, you can place. We can place 1000 divided by 75, which is roughly, I believe, 30. 1000 divided by 75 mm, which is roughly 30. Now, instead of 30, you make it as reduced to 12 because you cannot have 30 HS. So you make it as 12. So you will be having 12 tubes with 50 mm diameter. This is roughly equal to 600 mm. And 11 gaps with the 25 mm gap, which is equal to 11, 250, 225. Right? No, 275 mm. This is equal to 875 mm. Now, in this 1000 mm, 1000 minus 875 will give you 125 mm. 125 mm. You have to leave space on both sides. So 125 mm divided by 2, which is roughly 62.5 mm. Exactly 62.5 mm. This space you have to leave here. 62.5. Here it is also 62.5. Let us assume, yeah, here it is 62.5. 62.5 mm. On both sides you have to leave 62.5. So you get 12 numbers of cooling tubes. Now you can have 12 numbers here. And this side also you can have 12. This side you will be having only half of the quantity. So you will be having 24, maybe 6 or 6, which yields less than 64. So you may have to go for one more layer of cooling tubes, which means that instead of 12 tubes, you can make it as 11 tubes. 11 tubes which should be accommodated here. How we are going to accommodate here? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In between these two tubes, you have to make one more tube. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Similarly, you can make it as 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You make in between one each, which gives you 4, 5, 6, 7, 8, 9, 10, 11. Now in total we have 12 plus 11, 23, and here it is 23. So this is 23 tubes, another 23 tubes. This itself you have only 46, but your requirement is 64 or above, so you have to place it here. Now here also you can calculate it as for 500 mm. For 500 mm, what you have to do is 500 divided by 75, which is roughly 500 divided by 75, you get 6.6. 6.6, you make it as 5, which means that 5 into 50, which is equal to 250, and 4 into 25 space, that is 200, 4 into 5, sorry, 100. Yeah. 100, which is equal to 250 plus 100, 350 mm. So you have 500. I think you can have one more. If you want 6 into 50 is 300. 6 into 450, then the should be very small. Let it be like this. No problem. So 500 minus 350 will give you 150 mm. 150 mm divided by 2 will give you 75 mm. So here you can have a space of 75 mm. Here you can have a space of 75 mm. So here you can have totally 5 cooling tubes. 1, 2, 3, 4, and 5. Similarly here 1, 2, 3, 4, and 5. And another layer you can have it as symmetrical and also for your number of tubes requirement. So you have the total number of tubes. So let me write it down here. Total number of tubes is equal to, you have 2 into 12 plus 11 plus 2 into 5 plus 4. This is equal to 23. 23 plus 2, 46, plus 9, 18, which is equal to exactly 64 tubes. Of course, you can provide few tubes more. You don't need to provide anything lesser. So the total number of tubes, 64, is placed like this 250 kVA with a loss of 4800 watts.